So 10 years ago, almost 11 years ago, I had an opportunity to do a project with Google. At the time, I was sending spacecraft to Mars. The project was fun. It was being able to use Google's machinery to do Mars processing. And while I was there, Google said, hey, it looks like you're working on your dissertation. Would some computers make that easier? And I said, sure. And they said, here's 20,000, let us know when you're done. So they gave me an entire data center to do whatever I wanted to with. And it was so much fun that I didn't bother finishing my dissertation. And I went on and did cool, fun stuff with them. And that has turned into the project that I'm about to show you. Because I used to send stuff to Mars, I actually worked on Google Moon and Google Mars. If you've used Google Earth, these are modes inside of Google Earth that let you see the Moon and the Mars surfaces and rovers on top of them and that sort of thing. So I started off with what I thought was big data, but I was wrong. It was actually quite small data compared to what we ended up working with. So Google's mission is to organize the world's information and make it accessible and useful. And our mission is to do that for just a subset of the scientific data. So what that looks like to us is a bunch of data processing. And I'm going to tell you about one of the satellites we work with as just sort of an example of all the problems that happen along the way. So in 1972, the USGS launched Landsat 1, just called Landsat back then. And it was the first systematic observation platform for analyzing the surface of the Earth. Landsat data is a little tricky to work with. It's not really hard, but it's also not very easy. In addition to red, green, and blue bands, it also has near-infrared and shortwave infrared and some thermal bands. So it's a little bit of some complexity. But there's a lot of it. They've been collecting data since 1972, and the data became free in 2008, which, not coincidentally, is the same year that Earth Engine started as a project. Had the Landsat data not become freely available, we wouldn't have existed. When the Landsat satellites, there's now 8 Landsat satellites. When the Landsat satellites fly over receiving stations, they downlink the information that they've been collecting. And these dots are the various receiving stations around the world. And what was supposed to happen is that the receiving stations collect the data and then send it back to the USGS. And sometimes they did, and sometimes they didn't. But it turns out that over the course of the 40 years that Landsat's been collecting data, most of the data didn't actually make it back to the USGS. It's held in the ground receiving stations in various countries. About 50%, this number's gone down, about 50% of the data is not at the USGS, and they've then had a process where they're trying to get the data back in to make a complete archive. And this process has had some significant challenges. One of the challenges is that they were trying to get data out of Ecuador, and there was a governmental agreement. Yes, you can have the data. The data was being loaded onto ships, giant crates full of tapes being loaded onto ships. And actually the Army showed up and said, nope, you're not taking that data anywhere, and kept the tapes in the country. A lot of these tapes have been collected and stored in not particularly good conditions for up to 40 years. And so you might imagine in a place like Indonesia, when you don't store things particularly well, they get moldy and kind of icky. To read data off of a 35-year-old tape is, in and of itself, an interesting problem, but compound that with having to deal with mold and whatnot. One of the things you do to read very old tapes is you heat them up. So imagine a moldy tape that you stick in an oven, heating it up, it produces a significant amount of data, or a significant amount of toxic substances which you might not really want to be breathing. So they actually process these tapes in hazard suits because they're just not safe to be around. And once you heat it up and read it once, the tape's destroyed. So they have to be very careful with them to be able to get to this old data, which is now irreplaceable. the Landsat catalog contains now about 7 million scenes. It took us almost 4 years to get all the data out of them the first time, a little over 3 years. Because they keep their data on tape as well, and they process it on demand. So you say, I would like these 10 scenes, and they go off and they start processing them, and then they send you an email that says, your data is ready, which is great for 10 scenes, and it's okay for 100 scenes. It's pretty horrible for 1,000 scenes. We had to get 4 million out of them, now up to 7 million. So there was quite a big data challenge just getting to the data, let alone processing it. But once you have all that data, you can start doing interesting things with it. This is a picture off of the coast of South America. This is an actual scene from Landsat data that used to be the base map for Google Earth. So if you used Google Earth 5 years ago, this is what portions of South America looked like. Once you take all that data, you can now do some temporal compositing to try to remove clouds. So you can turn that image into that with just some processing, which looks like it might be useful. You can now get to individual fields. You can see the river, that sort of thing. This is a picture of one of the islands up in Great Britain. And again, when you composite together, you can actually bring a whole scene out of it. This is basically all the data. It took, in this area, which is cloudy all the time, it basically took all the data to be able to produce this scene. And so pixels over here might be from 1984, and pixels over here might be from 2008. And so maybe that's okay, maybe it's not. But it's one of the first times that you've been able to get a clear image of this entire area by compositing this data together. Here is all of South America. And again, you can process it into something nice and pretty. So once we got all the data out of the USGS, which was about 2 million scenes at the time we did this, 900 terabytes of data, took 2 million CPU hours to be able to process the data into cloud freeze composites running on a big cluster. We were going to do something with it. And since we're at Google, we made a video. And so you can see in this video some fuzzy bits. You can see it's kind of video-y, but that's not particularly impressive until I tell you that this is a 24 terapixel video. So this is a video of the entire planet at full resolution of Landsat for 30 years. So you can zoom in anywhere and see what's been going on in that location for the past 30 years. So this is Las Vegas. I'll just let you look at that for a second. In the past, at this point, it was 29 years. Las Vegas doubles in size over those 29 years, and this is Lake Mead, which is basically halved in size over the same amount of time. This is Saudi Arabia. In the late 90s, Saudi Arabia said, you know, we're importing all of our food. Maybe that's not a good thing. What can we do about it? So they put 2,000 farms in the middle of the Arabian desert, and they irrigate them from well water. They bring water up from the aquifer. And so they started growing crops. I like this image because humans have a word for what this is. This is terraforming. If we ever go to another planet, this is exactly what it's going to end up looking like. We knew that we'd see all kinds of human-induced changes over a 30-year time span, but these are the kind of things we never expected to see. So this is a river in Bolivia. This is a little town called Pucallpa, Peru. And that river moves as much as 1 kilometer a year in some cases. And this whole area is basically swamp. You know, the river moves around. You can see leftover meanders, and everybody knows rivers meander, but nobody expected to see it move at this sort of scale. And you can actually see there's a curve here where they knew the river was coming, right? That's where it stopped being solid, and the town grows that way. Like they knew not to grow this way. Additionally, we'll just stare at that for a second. So that's a phenomenon never before observed by a human. That's a new river being born. So we have some river morphologists that use our platform that are very excited about this because these are the kind of processes that they dream about, and now they can actually do direct analysis on top of them. So we made the video. We launched it with Time magazine called Time Lapse. you were actually able to embed those videos into your own website, and people did it. And any time that someone embedded one of those videos and then people looked at it, we would get a traceback. We would see a person coming from that site. And so we'd show up on a Monday morning, and there would be 30,000 hits from a little town in Ukraine. It's like, what's going on? And so you Google around and do some translating, and you see that there was a newspaper article that says, when the dam went in 1990, this is what happened to the town. And here's a link, and you can go see what happened. And everybody in the town would go follow that link and go look at their town and see what had happened. And so this is exactly what we were hoping for. People that would never know what Landsat is, never be able to download the data or process it, now have direct access to this data and can make use of it in their daily lives to make decisions about how to do their, how to govern their town. So it was a fun project. But so what? It was a fun project. Well, these guys are the Surui Indians. They live in that particular patch of forest in the Bolivian jungle. Excuse me, in the Brazilian jungle. They actually, this wasn't a staged photo or anything. They walk around with bows and arrows. One of their jobs is to keep people out of their reservation. The Brazilian government said, that land is yours, do what you want to with it. And what they want to do with it is maintain their Aboriginal lifestyle. So you can see in some cases there have been encroachments by logging into their area. This is all farm around them. It used to be pristine jungle. It's now subsistence agriculture or actually plantation. And they want to keep their jungle intact. And so they said, help us. Normally they're patrolling their area with bows and arrows to keep people out. But they said, look, you can see this stuff from space. All we need is a detector. You've got data, you've got processing. Help us build a deforestation detector to find where we need to spend our energies, because walking around with bows and arrows isn't working out so well. So, this is the entire time series in Rondônia. In the late 70s, Brazil put in these road networks that span the entire country in an attempt to get people to go out and colonize. And they do. You can see them go basically to the end of the road, start cutting down trees, building a farm. And it's their land, so you can't really fault them much for that. But after a few years, what happens is these subsistence farmers have only got a marginally better life than they had when they were hunter-gatherers in the jungle. And the plantation owners come in and buy them out. And so for $1,000, more money than these guys have ever seen in their entire life, they buy the land that the farmer has cleared, and it eventually becomes all plantation. And so the expectation is that before long, the entire belt of the Amazon here will just be one giant plantation for palm oil and soybean. So we built them a detector. It looks like this. I may actually get a chance to demo it for you, but the demo works exactly like this. Pick some data, identify some polygons as forest and not forest, and build a classifier. And it takes about that long too. So in about 30 seconds, we're able to build a binary map of forest and non-forest. It does an accuracy assessment. In this particular case, it was 92% accurate. But if you're the guy on the ground who's responsible for stopping the deforestation, and you see that there were trees here last week and there aren't trees here this week, this is good enough. You just want to know that piece of information so that you can go out and do some enforcement. The tool is unfortunately only in English, but even with that limitation, we built it in such a way that non-English speakers, in fact, completely uneducated speakers, completely uneducated forest rangers are able to use the tool to do what they need to do. We demoed this for the Minister of Forestry and Beekeeping from Peru. He came to our office and tried it out, and he doesn't speak English and we didn't speak Spanish. And in a few minutes, he got the idea and he says, okay, I know where the deforestation is happening, but these are illegal gold mines. Go find more of those. Those are what I need to stop. Mm-hmm. And so in a few seconds, actually, he was able to point out some gold mines and then find more of them. So it works. This is the king of the Surui, chief of the Surui. He's actually quite a politician. He goes out and does all kinds of work with the United Nations for indigenous people. And it turns out that his forest actually has really good Wi-Fi. All right, so why? You saw what we're doing with it, but why? We were a project started by Google.org, which is the arm of Google that is responsible for philanthropic efforts, as a public benefit project. The goal is to make it easy to do science and then operationalize it and run it at scale. And we have a bunch of goals, but all these goals basically boil down to building the world's most advanced geospatial platform, to be able to do things that just can't be done anywhere else. And so if we dive into that for a second, what does that mean to us? Well, we want to build the world's most advanced geospatial analysis platform so we don't all die. And this is a bit hyperbolic, and so maybe we'll just cross that out and say, to help solve the world's biggest challenges. And we really mean this. I'm going to show you an example, or a bunch of examples here in a few minutes about the big challenges that we're trying to tackle with this platform. Here's an example of a map we made in 2012 with Matt Hansen from the University of Maryland. It's the world's first map of forest gain and loss. So you can, again, go anywhere on the planet, look at full resolution of the Landsat data, whether or not forest is coming or going, and actually measure how much. And most of this is green, which means a little loss or no loss, but you'll see massive amounts of deforestation going on down here where it actually matters. In Indonesia, again, down in Brazil, lots of deforestation going on in southern Brazil. This is a project we're doing with the Desert Research Institute of Arizona. They're doing drought monitoring, but they're actually doing flash drought monitoring. So the project is doing evapotranspiration from Landsat data and being able to monitor the drought levels through how much water plants are transpiring. Turns out you can, on the order of a week or two, detect the occurrence of a drought, and so they're doing weekly drought maps. Right now for the US, but soon for the whole world. This is a project just submitted for publication. We're doing with the Joint Research Center, which is global water mapping. So not just where is the water now, but where has the water been for the past 30 years, and every month of the past 30 years, so that you can actually predict with some certainty about whether or not there's going to be water in that watering hole 20 kilometers away, where the rangeland, where the guys with cows in Africa need to go, right? They have to graze. There's not a lot of fodder in northern Africa. They have to graze their cattle quite far, and it's a complete matter of life and death about whether or not the watering hole they're headed for is going to have water in it. So if you have some accuracy in your predictions about which ones are going to have water in them, then you can do better rangeland management there. But it happens globally. We're doing a global crop map with the USGS. This is crop type, crop, non-crop, water, irrigation type, and then crop type. Hopefully they'll get to yield at some point, but they're not there yet. This is a project doing malaria early warning in Swaziland. So this is a predictive map of where it's likely mosquitoes will be breeding based on environmental variables. The intent is that the aid workers on the ground that have limited resources, like a finite number of mosquito nets, can use this map and a map of where aid has been previously distributed to focus their efforts to the places where it's most needed. So if you have two villages, both of which are at risk for a mosquito outbreak, and one of them has received mosquito nets and one hasn't, then certainly you want to direct your efforts towards the one that hasn't had mosquito nets issued. They're working on real-time alerting so that field workers on the ground can just use their phone to get maps like this. This is a project doing earthquake risk mitigation with a gentleman at Stanford. This is a simulated fault, and then a surface generated from that, or under that, that indicates how much ground movement there'll be if that fault erupts. And so basically it means don't live here. My house used to be right there. A map of global development. I'll actually show you this one live in a minute. It's a pretty map, but I think it will work better live. All right, so that's some examples of the things we're doing. That was, I think, 8 examples from 8 partners that we work with, and we have 14,000 of them using our platform. So this is just a very light sampling of what's going on. All of the people that use our platform are scientists. We only recruit at scientific conferences, AGU, EGU, LPS, IGARS, that sort of thing. And so we have currently been building a platform to engage scientists to make it easier for them to do their science and get their results to the people on the ground that need it. So what we are, if it's not obvious by now, is a big data platform for remote sensing data. And what that means to us is we essentially have an infinite number of computers. So we have a fast computation system and a visualization system on that. This platform is specifically built for geospatial analysis, and we have a very large scientific data catalog specifically for the purposes of having data ready to use. When you use us, it looks like this. This is a tool, the tool we call the playground. There's an interactive map on the bottom, a place to put your algorithms, inputs over there, outputs over here, very much like other interactive development environments, but this one's specifically tuned for making maps. I think I have a better one than that. Yeah. So our scientific data catalog is, as I said, quite large. Currently about 5.5 million Landsat scenes, almost all of MODIS, all of Sentinel-1, all of Sentinel-2, various other optical and thermal data sets, all processed to a ready-to-use form. Those are kept in a information preserving format, so they are in the original resolution, projection, bit depth with all the bands that they came with, but we made it fast to access them so that the platform can deliver results very quickly. We also have a bunch of other data, geophysical data, so quite a number of terrain projects, including a project where we're attempting to accumulate high-resolution DEMS for the entire globe. We currently have, I think, 1%, but we're working on it. Lots of land cover, croplands, surface temperature, various other data sets. We also have climate forecasts and hindcasts, ozone data, various precipitation data sets. These are typically used by people to remove atmospheric effects or to correct for recent rainfall or something like that. But a number of climate users have started showing up because this data is easy to use on us. 250 public data sets we update continuously every day, so we add about 6,000 scenes. That number is way out of date. We add about 6,000 Landsat scenes a day right now, and that doesn't include all the other data sets. Currently about 5.5 petabytes. So what does this thing do? I'm going to describe it in very simple terms and then show you an advanced set of uses of it. We've got this big catalog, and so one of the things you can do is just get an image out of the catalog. When you get an image, you can specify the projection, resolution, band, bounding box, and visualization. You want that in Albers equal area projection at 10 meters per pixel. Bang, there's your data. You don't have to do any processing to do that. You just ask for it in that format and it comes out. This works exactly like map servers, if anybody's familiar with map server technology. Then you can apply an algorithm to an image. So we have a library of functions, about 800 functions that you can chain together to build more advanced analysis with. But you get an image, you apply an algorithm to it, you get a transformed image. The data that are related to each other are kept in collections. So the Landsat data is in one collection, or 8 collections because there's 8 Landsat sensors. The MODIS data is in one collection, the Sentinel-1 data is in one collection. And you can filter this by space, time, or various metadata fields down to just the images that you care about. So if you want just the images from 2007 summer over San Diego, you just specify those criteria, and out comes the data that you want. You can map an algorithm over a collection. This is a computer science term that means apply a function to every element. So once you've got a collection and you have some algorithm that you want to apply to it, say a normalized vegetation index, you can apply that to every function, or every image in a trivial fashion. And this is an opportunity for us to do parallelism. So we spread, we can take that function and all the images that we specify it to, spread them out over multiple machines, process on multiple machines, and then collect the results back together at the end. This is where we start introducing advanced concepts to our users without them actually knowing what they're doing. They just say, here's my function, go do something with it. And behind the scenes, we deal with all the parallelism. They don't actually even get any control on how many machines, where they happen, how the data is distributed. The platform's all about hiding that from the user so that we can do it in the most efficient manner possible. We also have the other half of map, which is reduce, which is collecting a bunch of data together all at the same time and applying some statistical computation to it. So for instance, if you have a stack of Landsat images and you just want to squish them together into a mosaic, that's a reduction step. But alternatively, you might want to take the min or the max or the mean through the time series to then do further analysis with. So all those statistical analyses that go through the entire stack are a reduction step. And finally, we do various kinds of aggregates where you're doing something that is not so parallelizable. We find ways to make this easier, but for the most part, this is the kind of analysis where you want the mean of entire image. There's no fast way to do that except to collect all the data, process it, and get a result. All right, so there's stuff we're good at, there's stuff we're bad at. The things that we're good at are the things that are embarrassingly parallel. So per pixel operations, time series stacks, small neighborhoods. This turns into things like band math, spectral unmixing, machine learning classification, segmentation, template matching, and texture analysis. All those are very small operations where you can take a little bit of data, send it off to one machine, and have it process it, and have a million machines doing the same thing at the same time. The things that we're bad at are anything that breaks that. So anything that looks like finite element analysis, where a little change over here has to propagate through a bunch of iterations and can have an effect over here. That sort of iterative analysis is difficult on us, if not impossible. Especially iteration till convergence is just a thing that doesn't work on us at all. And so that means certain types of analysis, like hydrologic flow, we're just the wrong platform for. All right, so I'm actually going to do a live demo here. We'll see how that goes. Let's see. Okay. So this is our plan. Well, let me do this other one first. So this is the tool I showed you a minute ago. And what I'm going to do is a machine learning classification. It's going to take about as long as it did on the screen the first time. Let's go over here to Madonia. That'll work. We're going to grab some data. We happen to suggest to our naive users some composited data to work with off the top of, at the top of the stack. What these are annual composites that we've pre-built because they're easy to work with, and they're like the greenest pixel, or they're percentile composites. So if you take all the data at a location from, in this case, Landsat 7, and you stack it up and you sort it, the clouds are at the top of that stack, the shadows are at the bottom, and right in the middle tends to be the good pixels. So a 50th percentile composite, essentially a median composite, tends to work pretty well for most users. If you have more advanced cases, then there are other options. But if you're just trying to do annual type statistics, this works out as a pretty good answer. You can build custom composites if you don't like what we have. But I'm going to demo with one of these annual ones. Make this a little smaller so it's easier to see. So there's the data. So there's all the data from 2014. Let me find a better place. There we go, up here. I like this. So this is just a false, natural color composite. And what we have is, again, you can kind of see that, farming cutting into the rainforest. And so what we're going to do is we're going to add two data sets, or excuse me, two classes. And this one we'll call non-forest. This one we'll call forest. I can see pretty easily that this is all pristine forest out here, and all this stuff up in here is non-forest. I'm not being too careful. I'm going to train a classifier, and in a few seconds we'll have results. There's a list of classifiers to choose from. These are the ones that we think are most popular. And the thing about these ones in specific is that they're all popular enough that they all have their own Wikipedia page. So they're quite old. Many of them are quite old, but they're still sort of the staples of the remote sensing community. So in a few seconds, I now have a binary map that I can count pixels on. I've got an accuracy assessment over there based on the training data. Because I wasn't being very particular in the pixels that I chose, I have a fairly bad accuracy for my non-forest because there was a bunch of green under it. But I did quite good in the forest. And again, we call this the good enough map. It's the map that's good enough for the guy in the field to use to get something done. If for some reason you thought that elevation data would make your classification better, you can do a search. You might bring in temperature, surface reflectance, a bunch of data sets you can choose from. But I'm just going to grab one sort of at random here. Stretch it up so you can see it. That didn't work. Oh, that's the national elevation data set, so right. That's only in the US, that's not in Atlas. How about a little lesser? So nice elevation data. And now, just by bringing that in, I've added that additional data to my feature vector, and I can just train another classifier on top of that. These purple lines here indicate the data sets that are going into my machine learning feature vector, and then down there are the controls for creating and building the classifier that I want. And in this case, it got 6.6% better. Probably not worth it, but the idea is that we're essentially able to trick the user into being able to train up a machine learning classifier without them actually ever knowing that really that's what they're doing, except for the word down there that says classifier. All right, so that's our easy tool. And this is our hard tool. Before I jump into this, are there any questions yet? All right, I'll show you a couple of examples here, and then we'll see what happens. So this is, as I said, our exploration platform, our playground. It comes with a bunch of shared examples, so you can just grab some of these and use them to get started with. One of my favorites is this one. So I'll tell you about it, and then we'll look at it. So this is nighttime lights from the DMSP satellite. It collects data both day and night every day. At the end of the year, they composite all that data together into an annual nighttime lights composite, and that's what you're seeing here. This one's from 1992, but we have one for every year for the entire stack. One of the simplest analyses we can do is to do a linear fit at every pixel to plot the trend of nighttime lights. And that looks like this. So in this case, red is increasing lights and blue is decreasing lights. Green is overall brightness. And so general trends here is an increase in brightness in the past 20 years in Western Europe, decreasing brightness in Eastern Europe. Nothing's changed in Great Britain for 200 years, it's just bright. Way over here, yeah, there we go. So this is Japan. Again, it's just very dense and bright already. This is South Korea. This is North Korea. Everybody laughs at that. This is nighttime fishing fleets off the coast of Japan that use giant halogen lights at night to bring up the squid so they can harvest it. And it's diffuse and moves around because it's boats, they're not in one location, and it's blue because they don't do it so much anymore. So, lots of interesting data in here. Real quick, we'll jump over here. Various grid lines in the middle of America. This is interesting up in here. This is Alberta and up in Canada, Edmonton. Nobody lives up here, right? This is all oil flare from oil fields, all the way up, especially up in here, right? There used to be oil towns here, and the oil towns have moved as the oil has moved, or the oil extraction has moved. The blue on the coasts here we found quite interesting. We believe that that's stray light mitigation. So they're replacing old street lights, which have a lot of light pollution, with new street lights, because these are more or less the most affluent places in America, and we're pretty sure it didn't get darker there. It's just that they are actually spending money to stop the stray light pollution. All right, so again, an interesting map, cool stuff, but it's only 4 lines of code, depending on how you count. I count so that it's only 4 lines of code, but here's what it looks like. So these 2 bits here are just sticking things on the map and giving them colors, so we'll skip those for a minute. What we do is we get the collection of nighttime lights out of our catalog by name, and I happen to know its name, but you might not. But as you saw a minute ago, I can just start typing some thematic search term into our search thing, and nighttime lights is the first one that comes up. So there's a data set description, tells you about the bands, the units, various things you might care about the data set, and its ID. So that was what I was going to show you, is the ID. So there's the same ID that we're using in the code. There's an import button if you're not willing to cut and paste that, but you know, there it is. It has multiple bands, so we select one band, the stable lights band. We apply a function that gives every pixel both an x and a y value, because we're going to do a linear fit. We need a time of every pixel in addition to its value. So that's what this thing up here is. It's just basically a little bit of bookkeeping to get the date and stick it into every pixel. And then we run a linear fit reduction on top of that. So 6 lines if you count those, 25 lines if you count the whole thing, including comments and white space. But the whole idea is to be able to digest your problem down into bite-sized units, and each of those bite-sized units is a couple lines of code and 7 seconds to process. So you saw this come in when I loaded it, but I can change my analysis here and say that maybe my base goes from 2000 instead of 1991, and we click run, and in a few seconds I've got a new analysis. And so again, this is one of the places where we think our value is, being a fast, efficient platform for doing algorithmic exploration. It may be that you can chain together 100 of those 7-second processes, and so now you've got a 700-second process, but so be it. I can only make things go so fast. Again, when you can break your problem down into individual pieces, we try to make those individual pieces as easy as possible and as fast as possible. Another example, which you saw a bit of on the screen a minute ago, is, let's see, I was just there. Oh, actually, here, we'll do this one first. Come on, where are we? There we go. So we had a guy come to one of our workshops, and he says, I'm from the US Department of Agriculture. I have high confidence that if you're using center pivot irrigation in Iowa in July, you're growing corn. So I have an army of undergraduates clicking on circles on maps. Please help. So we'll think about it for a little bit. That's a pretty easy machine vision problem, just finding circles of a fixed size. What you're looking at here is a Landsat, one whole day of Landsat turned into enhanced vegetation index. So the darker the green, the more photosynthesis is going on. These areas that are circled but light are fallow fields, and in this area where there's nothing going on at all, it's just completely bare, or at least not photosynthetic. So we're just looking for these circles. So do a little machine vision, difference of 2 kernels, and that looks something like this. We'll keep loading here in a second. And that does a pretty good job in most cases, right? We're looking for circles, so these half circles didn't happen. This little pie-shaped guy is not going to happen. Come on, what's going on here? There we go. And it's got some problems because we're basically looking for things on a grid. If there's a square, and inside of that square there is a circle, it finds that. If it's neither, then you get garbage like this, right? You get things that are just sort of lumped on top of each other. So maybe not the best algorithm, but we can run another one. So the blue dots are a different type of machine vision, where we've run an edge detector, and now we're looking for rings. And those are, this particular analysis isn't going to be fooled by blobs of stuff over here. It's going to throw all that out. But there are other places where it does get fooled. I think they're up and to the right here. Zoom out a little bit. And it'll chew for a minute. But now I've got two different techniques looking for the same thing, and then science happens, right? I can compute probability. I can whatever I'm going to do. I've got multiple things to work with here, so that I can now I could here some smaller bits that are neither circle nor square show up in here. But the whole thing is again just a few lines of code. The first technique is convolution of a square kernel and a circle kernel and subtracting them, a little bit of thresholding to find what I want. And then the second one is edge detector, looking for rings, constructing the ring kernel, and then looking for it. So the whole thing, again, with putting things on the map, comments and splice spaces, 50 lines, it's really only about 10 lines of actual code. All right, I'll do one more example. And then we'll take some questions. So this one I'm actually going to have to hunt for a little bit. So let's start with the chart actually. So this is a bit more advanced. This is probably 100 lines in total. What you're seeing here is a year's worth of Landsat data turned into a vegetation index and plotted in blue. And then we've got code to do one frequency harmonic fit to that. Could be 2 or 3 just by setting them on. So this is the fit to this NDVI bit, this phenological series, assuming that there's only one growing season. You can in fact see that there's 2 here, so it's a bad fit, but that's sort of on purpose. If we make this 2 harmonics, then they fit a lot better. This particular curve comes from this particular point. This little field here, we've extracted the average NDVI out of it to do this. The image that you're looking at here is the grayscale underneath is threshold NDVI, but then the colors are the phase of that harmonic fit. So essentially, the color corresponds to peak growing season. Up here in the northern hemisphere, most of these colors are red and blue. If we go take the same analysis and look down in Rio de Janeiro, it'll all be blue and purple because the peak growing season is in our fall down there. So I like it because it's a pretty image, but it's also a fair bit of analytical analysis thrown together in some JavaScript, and you're off and running. We use this as a starting point for people when we teach. They'll say, okay, well, I want to do a sigmoid fit or whatever. This is how you get started on that. All right, I got dozens more examples, but we'll stop there for now and take any questions.
Thank you, Noel, for this talk. As you invited, are there any questions?
I have one. Is there any planned API to access, control, maybe automatically all the data, start some computation on the engine?
We have a thing that we're building called, give me a second. Event triggered analysis. So it's essentially a pub sub mechanism where you might subscribe to a collection. When the collection gets updated, that's an event. You'll trigger analysis looking through the new images in the collection to do whatever it is you're looking for, like deforestation detection. If none of the images fall into your area, you just shut down and you're done. If you find an image in your area and you run deforestation detection on it, you say, oh, there's a new deforested area, and then you can throw a new publication that says deforestation event, and whatever would be listening for those could then kick off. And start from there. So that's the closest we've got. I think that's kind of what you were asking about, yeah?
Yeah, that's right.
In works, not ready yet, but in progress.
Along the years, the spatial resolution changed, the spectral resolution changed with the Landsat images, and how do you deal with these heterogeneous data?
I have good news and I have bad news. The good news is we keep the data however the provider provided it. The bad news is that if you don't like that, you'll have to do some processing to convert it. So if what you want to do is spectral shift, then there's some spectral shifting algorithms that will resample the data into another wavelength set. But those are things you'll have to apply to homogeneous data sets. So if you want to bring in Sentinel-8 and Sentinel-2 and Landsat 8 data together, they don't exactly align. You'll have to do some shifting to make them align if that's what you need to do. If you're working on some kind of derived data like NDVI, that's a little less sensitive to those shifts. You're hopefully taking some of that out. There'll still be a shift, but the answer is you'll have to handle that yourself, but hopefully with the tools that we provide, you can do so.
Small question. The export formats for data is JSON. Are there other formats?
Import and export are both the same right now, geotiffs and shapefiles. So under the covers, we are a 2D gridded raster processing system. So we need 2D gridded raster data, things that are in a specific CRS. So pretty much all the data that we can handle will go through the geotiff format. So we just said, fit it in a geotiff and we're good. People ask us all the time, can you handle HDF? Can you handle NetCDF? Can you handle these weird Gaussian grid files? And the answer is, in some cases we can, but we generally would like the user to be more explicit about what you want to get out of that. NetCDF files can be a little complex, and HDF is basically a whole programming language. You can encode pretty much anything you want in an HDF file. So it's ludicrous to think that someone can just look at your HDF file and say, oh, you meant this gridded data set. In the process of making people fit into a geotiff, they've already taken the hard part out and just said, that's the data I want, stick it in. And the same thing out, right? This is a multi-layered image. You can export all those layers in either one geotiff or multiple geotiffs at one resolution or multiple resolutions. And the same thing for vectors. We have vector data that come in as shape files and go out as shape files. Also GeoJSON, but
maybe just the opposite question is, what kind of other data could be plugged in? Are all of the data sets capable of entering in the engine? Let's say number of mobile phone users, any kind of data.
So we have an upload button.
Compared to
basically anything you can fit into a geotiff is fine. We can't handle raw satellite data. If you're still in satellite coordinates, then that could be some crazy arc across the planet, or it might cover the pole, or there's all kinds of ways that raw instrument coordinates can be too wacky for us to handle. But once that's been reprojected into a specific coordinate system, we don't really care which coordinate system. It just needs to have a standard designator. Then we can understand it and process on it in a fast fashion. So what kind of data are you thinking of?
Well, I was just thinking of the compatibility between this and any other kind of more of a human users data, coming not from geolocated information, but from any kind of other information.
So we have census data, for instance, gridded population data sets.
And it's always based on location, I imagine. Yeah.
Pretty much everything's got a location. We do have data that's collected by users in the field. There's a whole other project at Google supports called Open Data Kit, which is essentially forms for your phone. and we teach people how to do in-field data collection. You build a form like you're going to go do a forest inventory. So you build the forest inventory form, which is, location, diameter, species, that sort of thing. So you go out in the field, you put in all your information as you encounter each tree, and that goes directly into the cloud as a point data set with all these pieces of information, and now that's a data set that you can use. Similar to buoy data or stream gauge data, but they all have a geolocation. Through vectors, you could probably do a lot of stuff that wasn't geolocated. For instance, you could have a vector table of spectral end members, which don't necessarily have a location. But then you need some way to you need to have a plan for what you're going to do with that, right? We basically produce maps, so you need somewhere along the way, some spatial information is going to come into it.
So maybe just to follow this question. So we talk about ground truth annotation as you presented for malaria detection or prevention in your first examples. So we could use this. We could use your tool for real-time annotation, and for example, people filling formulas and so on could upload directly all their data, and we could interact automatically on the system.
I think so. I'm not 100% sure what you're asking, but I think so. A thing I didn't show, but is quite common, is that lots of people put analysis systems on top of us. So there's a website called Global Forest Watch, and they took the forest cover and uncover map that I showed earlier, and they put a polygon drawing application on top of it. So you can say how much deforestation has gone on in this polygon, and we ship that off to us, we do the computation, and the result comes out. So we're intentionally built for that kind of lightweight interactive analysis where you might build the interface and just ask us to do the heavy lifting for processing the data.
You had some questions?
Yes, so this is a bit in relation with what was asked before, is that yes, you can input any georeferenced information, but it seems to be quite oriented towards rasters. So for example, if you have sparse data to inject into the system, you'd have to rasterize it, for example.
You can do vectors as well. So if you have a bunch of GPS traces or something like that, those come in as vectors.
Okay, good thing.
Other questions?
It's more about you're working for Google, and I understand that it's very interesting and all the capability, machinery that you're capable of using with them. But are there any inconvenience with working with such a big company?
Oh yeah, it's a big company.
Yeah.
Well, I have lots of anecdotes. I don't know if they're counted as data. When I started at the company, there were two people between me and the CEO. There was one person, my VP, and then Larry, the CEO. There are now 11. 12 now that he's moved out and is overseeing Alphabet. And so now, it's just a matter of the fact that the company is much larger. There were 15,000 people when I joined. There's now 70,000 or so. We've got a lot more vertical. There's now actual management stuff that happens. Just all the stuff that you expect when you've got 70,000 people and you're trying to keep them all kind of pointed in the same direction. That said, I said, hey, I'd like my office to be in Zurich, and they said, sure, click the button. They moved my office. So there are definitely advantages to it in a big company. But yeah, there's a lot of procedure and process that is in there to try and help you, but sometimes gets in the way. Yeah. No, one more.
There is no.
You're it.
Yeah, no, just the last question about, there are many things that are unmappable, I imagine. what is your dream or ambition to map something that you are unable to do for the moment?
So let me answer a different question and see if this sort of gets to what you're trying for. The reason we exist is because we believe that there are certain levers on society that if you can just push on them a little bit, they'll have huge impacts. For instance, if you can increase global crop yield by 1%, which is probably not out of the realm of possibility just with mapping, right? Give everybody better maps, tell them where they need to fertilize, where they don't need to fertilize, where the water needs to happen. Some precision agriculture just spread over the entire world. That's actually probably more like a 5 or 10% increase in global crop yield. That's now affecting millions of lives and is worth billions of dollars. Agriculture is 3% of global GDP, and global GDP is 80 trillion, if I remember that right. So it's 1% of 3% of global GDP is still a big number. So there's a lot of interest in pushing on that lever, not just for the fact that somebody might make some money along the way, but decreasing global food, or increasing global food security by that much is a valuable thing. That's just one little vertical in which there are many. If you can decrease global disaster costs by 1%, again, that's affecting millions of lives and billions of dollars. And so I don't know what the maps are that will cause that to happen, but I know the guys that are trying to work in those areas, and I know that they are often limited by whether or not they can have an accurate map, whether they can process the data and get the map out. So my goals and my whole team's goals is just to give those guys the tools so they don't have to worry about data processing and downloading and file formats and all that garbage that's just IT. We can handle it once, they just show up and they actually get something done, and they're off actually solving global food security instead of dealing with how many disk drives they need to buy this month to be able to process that data. So not exactly what you were asking, but close.
Yeah, interesting. Thank you.
All right.
One more question? One last question? So, just to finish, so your solution is pretty impressive, but if we want to, so there are plenty of different use cases, the most basic one being able to download a data set in a more easier way than contacting ESA and company.
Yeah.
But what are the limits? Say, so it's always heavy to download data, but do you impose some limits?
Yeah, first of all, let me show you how easy it is, and then we'll discuss what the limits are. So let's pretend this is a data set I want. What I can do is I can draw a polygon. This is a composite of a bunch of Landsat data. So let's say that's my area. That's about the size of California, give or take. Down here at the bottom of my script, I can just say export image, and my image looks like fitted. And I'm gonna click to my geometry. So what that should do is it should generate a task over here. If I didn't have an error, which I do apparently. Geometry. So that generates a task over here that, all right, maybe it doesn't. All right, one more time. Turns out this is an image collection, not an image. All right, one more. There it is. So there's my export task that would export the stuff inside that geometry. So I can specify, there are lots of parameters I specify on the way. But, so you can kick this off and we'll dump it to one of these 3 places. And you can have 20 of those running at a time. And so you can basically do a 20-way download, 20 simultaneous downloads through that mechanism. If you're not trying to do, there's a lot of processing involved in this with the harmonic fitting and whatnot. If you're just trying to get a sentinel image, for instance, that'll go much faster. And there's actually a command line tool where you can just grab something out of a collection and export it semi-directly. So you don't have to go through the GUI. The GUI is really just a thin wrapper on top of the API, so you can always call the API directly. The command line tool makes it even easier to do that. So 20 at a time, I guess, is the answer.
Okay, impressive. So yeah, all of the tools we propose for, I can imagine that we could do everything on board on your system, but I already asked you, can we do TensorFlow, which is also a Google product?
This summer, we're actually working on tools to make this whole flow a lot easier, specifically for doing TensorFlow on something like Compute Engine. So a big bank of computers, whether it's ours or Amazon or yours, being able to pull out essentially chips that you might do a convolution network on top of. So how to get those out at a fast rate. It's still, if you want a terabyte of data, it's still a terabyte of data. So I don't know how fast your internet is here, but in most of the world, that's still a couple hours. So I can't make your internet faster, but I can certainly make it not waiting on us.
So impressive. Thank you. Are there any more questions? No? So maybe let's close the seminar. Thank you again, Noel.